Today we will discuss the evaluation of Lagrange's undetermined multipliers. Basically, we will determine alpha and beta. Since we know from the previous knowledge that the total number of particles is basically equal to summation of ni particles. Suppose this is our equation number 1. Also, from Boltzmann distribution law, which says that the ni is equal to gi e raised power minus alpha minus beta ei. We derived this relation in Maxwell-Boltzmann distribution law. So this basically gives the most probable distribution for a macro stage. So suppose this is now equation number 2. Now what we will do, we will take the value of ni of equation number 2 and put it as value in the first. So it will imply that n will be equal to summation I gi e raised power minus alpha minus beta ei. So this is our equation. We have done nothing, we have simply taken the value of equation number 2 and put its value in the first. So we got this equation. So this relation can also be written as n will be equal to summation I gi e raised power, we will separate these two, minus beta ei multiplied by e raised power minus alpha. So from this equation we will get this equation that e raised power minus alpha will be simply equal to n upon summation I gi e raised power minus beta ei. So this is now our equation number 4. So basically we will now define a quantity q. It is simply called, q is called the molecular partition function. Now this q is, we will define this, q is equal to summation of I gi e raised power minus beta ei. That means this part, the division part of equation number 4, we will take it equal to q, simply the molecular partition function. Now this is suppose now equation number 5. Therefore, from equation 4 and 5, we can write e raised power minus alpha will be equal to n upon q. Simple. This is equation number 6. It will also imply equation 2 can therefore also be written as. So in place of summation gi e raised power minus beta I, we will put, or in place of e raised power minus alpha, we will put the value of n upon q. So we will get this equation. That means the ni will be simply equal to, in place of e raised power minus alpha, we will simply write n upon q, and multiplied by, it is simply multiplied by gi e raised power minus beta ei. So this is our equation number 7. Okay. So the partition function which we represented with q is a quantity of immense importance. In statistical thermodynamics. Why? Because by simply evaluating the q, that means the partition function, molecular partition function for a system, we can calculate the value of any thermodynamic function for that system. That means if we simply know this molecular partition function, we will be able to calculate various thermodynamic functions of a particular system. Okay. Now we will see determination of the constant beta. We will determine its value. For Maxwell-Boltzmann statistics, the thermodynamic probability, we have already derived this thermodynamic probability, so we will give here simply the equation for the system which contain n particles. That means we will simply write that equation here. W is equal to n factorial pi I gi ni upon ni factorial into constant. So this is our equation number 8 basically. So taking log on both sides and applying Stirling approximation, taking logs and applying Stirling's approximation, to equation above, that means equation 8, and this Stirling approximation is applied to basically ln of n factorial and ln of n I factorial. So we will simply have ln of w will be equal to ln of n factorial. Pi will change to summation. We will write summation outside, so it will be log of m raised power n, so it will be ni gn. So we will simply write it as ni ln of gi. So this is in division, it will be log of m upon log of n, that means log m minus log n. So it will be minus here minus ln of ni factorial plus simply constant. So this is our equation number 9. This can be now further solved by using the Stirling approximation. Applying Stirling approximation first to this one, it will be n ln of n minus n plus summation I. We will write summation outside for both the terms and first solve these two with Stirling approximation. That means it will be same here, ln of gi. Now it is minus outside, it will be minus ni ln of ni minus minus, it would have been minus ni, so but minus was outside, so it will be plus ni plus constant. So this is equation number 10. Further, this can be also written as n ln of n plus, you have to see here, if I give summation back to this term, summation I ni, it will be equal to n. That means we know summation I ni is basically capital N. So this is plus n, this is minus n. So these two terms will go. It will be summation ni ln gi minus summation. So I will write the rest terms here. Summation I, or we can first solve it fully. Ni ln gi minus summation I ni ln ni plus summation I ni plus constant. Now it can also be written as n, but it would have been here minus n. n ln of n minus n plus summation I ni ln of gi minus summation I ni ln of ni. So in place of this term I will write simply plus n plus constant. So I was talking about this one, this n and this n will cancel. So I will get simply now this equation, n ln of n plus summation I ni ln of gi minus summation I ni ln of ni plus constant. So this will be equation number 11. So if we take the equation number 7 here, taking log of equation 7, which is basically, I will write it here once again, ni is equal to n gi e raised power minus beta ei upon q, because e raised power minus alpha is basically equal to n upon q. We have done this. So if we take the log on both sides, so it will imply ln of ni will be equal to ln of n minus if you take the q to the numerator, it will be ln of minus ln of q, it will be plus ln of gi, and log and exponential will go, it will here simply be minus beta ei. So this is equation number 12. Substituting in equation 11, that means we will take the value of ln of ni and put it into equation 11, this equation here, this is equation number 11. So we will get ln of w will be simply equal to n ln of n plus summation I ni ln of gi minus summation I ni. I will write outside this term, and in place of ln of I will write the remaining terms here. It will be ln of n minus ln of q plus ln of gi minus beta ei. So it can also be written as n ln of n plus summation I ni ln of gi minus, so what we do, we will give summation back here. You know summation I ni, it will be simply equal to n here. If for the first term we will write it as ln of capital N, then plus here again, because minus minus will be plus, so summation of ni will be capital N ln of q, plus we will retain it here, sorry, this is plus minus will be minus here, this minus and this plus, it will be minus here, minus summation, we will retain it as such, ni ln of gi. Again minus minus will be plus, plus, and beta is simply, we will take it outside, we will simply write it as summation ni ei. We are just multiplying this term to the all the terms. Okay, here you will see this n ln n and minus ln n, it will go, also this term minus summation I ni ln gi and summation ni ln gi, they will cancel out. So we will get now a simplified equation, which is basically ln of w will be equal to n ln of q, this term here, and simply plus beta. Now only this term remains here. You know summation ni ei is basically equal to the total energy. You can write it as u or capital E, so I will retain it as u here. So this will be our equation number 13. This is the simplified equation. Now substituting this result into the Boltzmann equation. Simple Boltzmann, that means we know that entropy is simply S is related to K ln of W. This is simple Boltzmann equation. So in place of ln of W, we will use this equation number 13 here. So S will be equal to K, or you can write it as improperly Nk ln of Q plus K beta U. This is equation number 14. We have simply put the value of ln of W here as n ln of Q plus beta U here. So this is. Now also we know from the combined, basically from the combined statement of the first and second laws of thermodynamics. We know that for a simple, that change in total energy is basically equal to TdS minus Ed. This is equation number 15. Now at constant volume, we know when V is equal to constant, dV will be equal to 0. So therefore equation 15 then can also be written as, we will write it as in terms of partial dou S upon dou U at constant volume will be equal to, because this term will go, this will be equal to 0. Here we will write as dou S upon dou U, it will be equal to 1 upon P. So this is equation number 60. Now if we take equation 14, the above equation differentiating equation 14 with respect to U at constant V cat. Equation 14 is basically S is equal to Nk ln of Q plus K beta U. Now we have to basically differentiate it with respect to U and keeping volume constant. So what we write here, we will write it as dou S with respect to U at constant volume will be equal to Now we have to differentiate with respect to this differential of, differential of, when we differentiate ln of q, it can also be written as 1 upon q dq. So we will use it here. We will write it as nk upon q and dou q upon dou u at constant volume, plus it will be k beta, and it will be it is basically the uv function now. So we will first keep this kb outside and differentiate it with respect to, so it will be dou u upon dou u, that means simply equal to 1 plus ku. K is constant, so we will take it outside, so it will be simply next v function will be dou beta upon dou u at constant. This dou u upon dou u will be simply equal to 1. You can write it as nk upon q. Suppose we multiply dou beta in the numerator as well as denominator of this equation here, so we can also write it as dq upon d beta, or we can write it as dou beta upon dou u at constant volume. What we have done, we have simply multiplied in the numerator as well as denominator the dou beta. Okay, plus it will be simply equal to k beta, this term, and plus ku, and it will remain as such, dou beta upon dou u at constant volume. Suppose this is equation number 70. Now from equation 5 we know q is equal to, that means partition function, basically we have written it as summation gi e raised power minus beta ei, and if we differentiate this with respect to dou beta, that means it will be dou q upon dou beta. It will be equal to, here you will see this is uv function again, so we will write summation outside and simply differentiate the other part, d e raised power minus beta ei upon d beta plus e raised power minus beta ei dgi upon d beta. This will be equal to 0 because it is gi with respect to beta. There is constant, you can say, and it will be equal to 0. Now remaining this term, this can be written as summation I gi, differential of e raised power ax will be equal to a into e raised power x. You can use that function also here, so it will be minus ei into e raised power minus beta ei, or you can simply write it, you can take minus outside, so you can write it summation I gi e raised power minus beta ei, and it will be again, now here it will remain as e, you can write it as summation ei. We can multiply in the numerator as well as the denominator by summation ni. Why? Because summation ni ei is basically equal to u. We have to make it like that, so this will turn out to be dq upon d beta will be simply equal to, minus is outside, you can replace this as with q, this term, and the above term as with u, and it will be summation of ni will be equal to simply, and so it will be u into q upon n. So we got this relation. This is simply equation number 18. Now substituting equation this 18 in equation 17 results in basically cancellation of the first time and the last terms. It is very simple. Now you will get simply dou s upon dou u at constant volume will be equal to k beta. So this is our equation number 19. If we compare this equation, comparing equations basically 16 and this 19, so the dou s upon dou v part is same, so we can simply write it as equal to 1 by t. 1 by t will be equal to k beta, or we can write it as beta is equal to 1 upon kt. So you have to remember, for all the statistics we have discussed, whether that is MB, FD, Maxwell Boltzmann, Fermi-Dirac, here all the three statistics, their beta value is basically equal to 1 upon kt. Okay. So this will be our equation number, suppose 20 now. Hence, from equation 5, where we introduced the molecular partition function, so q can also be written as summation of I gi e raised power. So in place of beta you will simply introduce the value 1 upon kt, that means ei upon kt. So this is equation number 21. And also the Maxwell Boltzmann distribution equation, which is given by equation number 7, then that will become ni will be equal to n gi e raised power minus ei upon kt upon q. So this is equation number 22. So from equation 22 we can easily obtain the ratio of populations basically. So if sometimes a question is asked on the ratio of populations, so we can ratio of populations, so we can transform this equation 22 as, suppose we have number of particles in any two energy levels, those are represented as ei and ej. We will simply write it as, first, suppose first was ni, will be simply equal to n gi e raised power minus ei upon kt whole upon q. And suppose we have nj particles, those will be equal to n, we will be seeing gj e raised power minus Ej upon kt whole upon q. When we take the ratio of these two, that means we have to divide this n and n will go, this q and q will go, and you will get this type of equation. That means we will get ni upon nj is basically equal to gi upon gj e raised power minus ei upon kt, and this is divided in e raised power ej upon kt, then it will be plus. That means we can write e raised power plus form ej upon kt. This is ei, it is ej. So we can also write it as gi gj. Bases are same, powers will be simply added. So we can write simply this form of equation, that means minus ei upon kt plus ei upon kt. If bases are same, we can take the base and we can also take the negative outside. So we will simply write it as ni upon nj will be equal to gi upon kj e raised power minus, we will take the negative outside, so it will be ei minus ej upon kt. So this is equation number 23. So this equation number 23 basically which is easily obtained from the ratio of population, that the number of particles into energy levels, can be simply used to calculate the population of states. Okay, thank you.